The time I was there, my dive to the Titanic only lasted 37 feet down, and then it had a mechanical problem and had to be hoisted back onto the ship. This sub, as you sign on the waiver, you say, I understand that this sub has not been inspected or certified by any third-party body.
Let's venture into the ocean's depths, where a brave journey to uncover the secrets of Titanic's wreckage went tragically wrong. On June 19th, a journey was embarked upon to solve the mysteries concealed beneath the northwestern Atlantic's waves. The OceanGate Submersible was given the responsibility of diving deep into the sea, moving down at 55 meters per minute. As it went deeper, it was confronted with an enormous challenge in the form of crushing pressure. The submersible's hull fought against the intense forces that threatened to crumble even the strongest structures. At a depth of 3,800 meters, the submersible would be under the weight of 366 Earth atmospheres. To prevent confusion, let's ensure we have a shared understanding of implosion. It's when an object collapses inward, unlike an explosion that expands outward. The Titan submersible imploded instantaneously due to the enormous water pressure surrounding it. With the help of a verified communication transcript between the submersible and its surface support vessel, we can trace the adrenaline-filled moments during this inconceivable catastrophe. Join us as we read through this transcript, glimpsing into the chilling exchanges that occurred in the deep. Before we delve into the specifics, let's differentiate between a submersible and a submarine. A submersible is usually launched from a larger mother or home vessel. It is placed on a platform or raft and submerged in the water. In contrast, a submarine can dive underwater without additional equipment and resurface using its buoyancy control system. Now that we understand the key differences between a submersible and a submarine, let's focus on a specific submersible, the Titan, and examine its details closely. Despite its small size, the Titan weighs around 9,525 kilograms or 21,000 pounds. It's roughly 22 feet long, which is about 6.7 meters, and it's around 9.2 feet wide or roughly 2.8 meters. Its height is approximately 8.3 feet or 2.5 meters. To give some context, think of how it compares to an average human. Visualizing it next to a small SUV helps illustrate its size. It's designed to endure massive water pressure at depths up to 3,800 meters, or roughly 12,467 feet below sea level. That's akin to the weight of the Eiffel Tower pressing down on it. This submersible is engineered to withstand such conditions, with a hull that is believed to have been constructed to resist these extreme pressures. Let's take a closer look at Titan's structure and how it works. The submersible was created in a cylinder shape to make room for more people. It can carry up to 5 individuals, including 1 pilot and 4 passengers. However, due to space limitations, the passengers must sit on the floor throughout the trip. And yes, there's a toilet inside the submersible, hidden behind a curtain for privacy. The pilot, sitting at the front, guides the craft using a joystick, moving it forwards, backwards, or turning as needed. 2 screens offer vital visual information. Titan's interior design highlights simplicity and function, considering the limited space. A carbon fiber tube was placed between 2 titanium ends. This carbon fiber is incredibly strong, used in making airplane wings and racing cars. But does it also have the toughness and appropriateness for submersibles? Keep watching until the end of the video to find out. In the final segment, I'll reveal the faults and the events leading to the disastrous failure. The journey starts with the mothership, known as the Polar Prince, anchoring at a spot near the Titanic wreckage. A ramp linked to the mothership is lowered, letting the Titan submersible slowly sink into the water. Once it hits the required depth, the submersible detaches from the platform and begins its exploration journey. Titan's propulsion system is made to navigate the demanding underwater environment. The submersible comes with 4 electric thrusters vital for steering. 2 thrusters are positioned horizontally, while the other 2 are placed vertically on either side of the vessel. It can reach impressive depths of up to 4,000 meters, 13,000 feet, and speeds of 3 to 4 knots, equivalent to 3.1, 2 miles per hour, despite the deep sea's high pressure and density. The back of the submersible houses electronic devices including oxygen and navigation systems. Moreover, this unmanned section can recycle carbon dioxide and produce oxygen for the cabin, providing a 96-hour oxygen supply. However, Titan's journey to the Titanic was marked by a tragic event. During a descent into the Titanic wreck, communication with the submersible was lost. It was later determined that Titan had suffered a disastrous implosion, a sudden inward collapse due to the weakened carbon fiber hull, sadly resulting in the loss of all 5 passengers on board. From the information I gathered, the key design aspect of OceanGate's Titan submersible was its composite hull, made of titanium end caps and composites. These consist of fibers bonded together by a material such as epoxy, resulting in variations in fiber direction and the existence of voids or unfilled spaces. While software simulations can help examine specific failure modes, real-world testing is vital to confirm and refine these models. OceanGate's decision to depend solely on computer modeling without thorough physical testing, plus their choice to cure the composite hull without using an autoclave, a pressurized oven that helps remove voids in the epoxy resin, raises concerns about the existence of porosity and defects. Spencer Composites, the manufacturer responsible for the hull, claimed that the porosity was less than 1%. However, the lack of detailed information about the actual porosity level leaves room for doubt. Despite these possible issues, the Titan submersible was different from traditional submarines made of steel or titanium. Titan utilized experimental materials, primarily carbon fibers. These carbon fibers are lighter than titanium or steel. Carbon fiber composites are best known for their tensile strength, making them appropriate for uses such as pressurized aircraft fuselages. In these situations, the pressure inside the fuselage works to expand the circular cross-section, putting the fibers in tension. However, in a submarine, the pressure would act to compress the hull, subjecting the fibers mainly to compressive forces. However, using carbon fibers in such a high-pressure environment is not without danger, and we still need a full understanding of how they behave under such intense pressure. The carbon fiber hull can suddenly crack or break, resulting in structural collapse under high-pressure conditions. Rush defended the use of carbon fiber, asserting it is 3 times better than titanium regarding strength to buoyancy, which is vital when underwater. Submarines like Titan, aiming for neutral buoyancy, strive to displace water with a weight equal to their own, reducing the energy needed for vertical movement. The lighter weight of the carbon fiber composite aids in achieving this neutral buoyancy goal. However, the choice to skip the foam outer layers typically used in submarine hulls to attain buoyancy raised further concerns. So the manufacturing process must be closely watched to avoid any disastrous failures. The Titan submersible did not use the foam outer layers commonly found in submarine hulls. According to OceanGate's CEO, Stockton Rush, the choice to omit the foam layer was motivated by cost considerations. While cost optimization isn't inherently problematic, it becomes questionable when the composite's structural integrity is unsure. OceanGate's reasoning for not subjecting their submersible to testing by a regulatory body adds to the doubts surrounding their engineering decisions. Instead, they used a carbon fiber cylinder, a troublesome structure developed in partnership with Boeing. The submersible's domes were crafted from 3¼ inch thick titanium. The carbon fiber was glued to a titanium face, an interface, and the dome was assembled with tight tolerance on the surface. The submersible was also designed such that no pipes, wires, cables, or tubes went into the carbon fiber part. However, concerns arose about the absence of comprehensive testing and certification procedures. Reports suggested that the carbon fiber used to construct the Titan was purchased at a significant discount from Boeing because it was past its shelf life for airplane use. This decision raised concerns about potential defects in the material that may have contributed to Titan's tragic end. Moving away from initial concerns, let's explore the company's view on industry standards. In a blog post that has since been removed, OceanGate expressed its belief that industry standard classifications, ensuring compliance with accepted standards, did not adequately address operational risks. While it's true that many accidents in marine and aviation industries are due to operator error rather than mechanical failure, the lack of rigorous testing and certification procedures heightens the chances of overlooking catastrophic failure modes in the design. Despite the company's stance on industry standards, there were significant warnings that were ignored. OceanGate was cautioned in 2018 that a lack of third-party scrutiny of the vessel during development could result in catastrophic safety issues. In a court case, a former employee named David Lockridge accused OceanGate of not adequately checking for delaminations and voids, leading to his firing shortly after raising these concerns. He championed for non-destructive testing methods, such as ultrasonic scans, but the company rejected this. OceanGate had its own counter-arguments against these warnings, mainly focusing on the limitations of existing technology. OceanGate maintained that the technology to inspect for voids and delaminations in a composite of this thickness was non-existent, so they depended on an acoustic monitoring system to anticipate failure. However, using such a system with a carbon fiber composite isn't sufficient due to their sudden and devastating failure characteristics. But these technical arguments don't fully consider the specific hazards related to composite materials. One particular failure mode, snap buckling or delamination, presents a significant danger for composite materials in deep-sea settings. The Titan used an acoustic monitoring system to listen for sounds made by the carbon fiber that might signify potential failure. Sadly, despite these safety measures, a tragedy occurred an hour and 45 minutes into the dive, at the ocean's bottom. Unfortunately, during its mission, the submersible didn't make it to the Titanic wreckage. The OceanGate Submersible lost contact with the surface, leaving those above with a deep sense of dread. Later, it was disclosed that the submersible had imploded, a sudden and catastrophic collapse. This dreadful accident, while tragic, wasn't entirely unexpected. The implosion was due to the weakened carbon fiber hull. The design of the Titan itself played a significant part in the disaster, largely due to the increased external pressure. This design meant that the Titan encountered more external pressure, making the cabin space longer. In a submersible, this increases the pressure in the middle sections, which can lead to more wear and tear and potential layer separation of the material. Wear and tear can be likened to bending a wire back and forth until it breaks, while layer separation is similar to splitting wood along the grain, which is easier than cutting across it. This unfortunate event drew attention to the vessel's construction timeline. Remarkably, the hull was built in just 6 weeks, a fact now under investigation as a crucial element in the disaster. Composite material engineers, familiar with the properties and limitations of such materials, could have predicted this failure. The ability of carbon fibers to endure repeated stress cycles, particularly compressive stress under deep-sea pressures, is not well understood, making it difficult to design safe hulls based on carbon fibers. One instance of this challenge is evident in Titan's hull. The Titan's hull, a 5-inch thick structure, had been subjected to repeated stress over about 24 prior dives. Each dive would place immense pressure on the hull, causing tiny cracks to form in the structure. These cracks, though small and unnoticeable initially, would eventually become critical and lead to rapid and unmanageable growth. According to Jasper Graham Jones, an associate professor of mechanical and marine engineering at the University of Plymouth in the United Kingdom. To address this issue, non-destructive testing methods like ultrasonic scans are utilized. It can help identify areas within the structure where the composites are separating. This kind of testing is essential for assessing the durability of structures under stress. The Marine Technology Society, a group of ocean engineers, technologists, policymakers, and educators, also expressed their concern to OceanGate about Titan's size, the construction material, and the fact that the prototype wasn't being inspected by a third party. They worried that without a proper certification process, essential safety aspects might be overlooked. However, not everyone agreed with this approach. Despite these warnings, OceanGate criticized the third-party certification process as time-consuming and hampering innovation. But experts in the field argue that seeking outside expertise to ensure vessels meet the highest industry standards is standard engineering procedure. OceanGate Expeditions charges a minimum of $25,000 per trip to the 1912 wreck site. The firm has experienced a string of mechanical issues and harsh weather conditions that have resulted in trip cancellations or delays in recent years, as per court records. Last week, a transcript of the communication between the OceanGate Titan submarine and its surface support vessel, Polar Prince, appeared online. "We can't verify its authenticity, and opinions are divided. Some consider it to be genuine, while others label it as a fabrication. With this background, we will analyze the transcript, look into the details, and decide on its credibility. The transcript starts with polar prints giving the Titan the go-ahead for the descent. The Titan confirms it is going down, and everything seems standard so far. Polar Prints checks in from time to time, asking for updates on Titan's depth and condition. However, about 20 minutes in, the surface vessel asks the sub to check its systems. The sub confirms that everything is running smoothly and continues its descent as planned. Examining the descent, we notice a thrilling detail we would like to mention. The sub might be descending too quickly considering the depth it needs to reach and the time it usually takes to descend. According to information from James Cameron and OceanGate's website, it should take approximately 2.5 hours to reach the Titanic shipwreck. This translates to an average speed of 25.33 meters per minute for the sub. Building on this observation, we encounter the first hint of trouble. The Titan reports an alarm from the real-time monitoring system, RTM, and slows its descent velocity. Following this issue, we shift our focus to the descent speed. At this point, their depth is reported as 34.33 meters, but according to our calculations, they should only be 22.29 meters. The sub is now 1,200 meters deeper than expected, confirming our suspicion that it is descending too fast. With the descent speed in mind, we draw our conclusions. The reported depths consistently exceeded the expected depths at specific time intervals. This discrepancy aligns with our earlier observations and calculations. The situation worsens when we realize they were alarmingly close to the Titanic shipwreck much earlier than expected. The Titan then reports that, despite no change with thrust, the rate of descent is increasing. The situation escalates as the Titan reports multiple attempts to jettison the frame, a slow ascent, and a crackling sound from the AFT. The RTM alerts are all red, indicating a severe problem. The Polar Prince tries to assist, asking for updates and discussing the situation with an engineer. However, the Titan reports more sounds from the AFT and a red reading on the A power bus. The crew switches to the B power bus. The Polar Prince continues to request updates, but the communication from the Titan becomes increasingly sporadic. The last few entries from the Polar Prince are requests for a response from the Titan, but no further communication from the submersible is recorded. It's disheartening to see that the real-time monitoring system, which was supposed to detect any hull defects before compromising crew safety, failed to provide accurate information in this particular disaster. The Titan, made of carbon fiber, was lighter than the water it displaced. This design choice might have contributed to the disaster. The submersible's weight distribution could have been affected by this design, leading to difficulties in maneuvering and controlling the vessel's ascent and descent. This could be a sign of the carbon fiber hull failing under the immense pressure of the deep sea. Carbon fiber, while strong, can have a catastrophic failure if there are imperfections in the structure. The sound of crackling could have been the fibers snapping under stress, a clear indication of an impending disaster. Interestingly, this wasn't the first time such a sound was reported. During a test dive in the Bahamas, an expert could audibly hear cracking sounds, indicating accumulating damage. Despite this warning, Stockton Rush chose to ignore the expert's advice, emphasizing the disregard for safety concerns. The growing alarm from the submersible, evident in the transcript, paints a dire picture. The crew was aware of the issues they were facing, but their options were limited. The lack of information from the submersible in the final moments only adds to the mystery and tragedy of the event. Speculations arise about the possible causes of the disaster. Some suggest compromised power systems, while others point to water leakage into the sub's rear section. While this transcript could be genuine, it's essential to await official confirmation and investigations to ascertain the truth. However, there is one important question that remains unanswered. Do you think OceanGate's decision to use carbon fiber for the Titan submersible instead of traditional materials like steel or titanium was a bold innovation or a reckless gamble? We'd love to hear your thoughts on this in the comments below. If you like this video, please give it a thumbs up. And like always, with that said, thanks for watching, and until next time.